Okay, let's do mechanics number 6. Mechanics number 6. Okay, you can see where we're going with this. And for my money, we're starting physics actually now. What we've learned so far is problems, kinematics problems, how to figure out where something is after it's been such and such acceleration, starting velocity, amount of time, or final velocity, all these things. We've been doing kinematics problems, but what we have failed to explain is why things move that way in the first place. And that's important. Why do things end up getting going? This is where Isaac Newton, brilliant Isaac Newton, applied his 3 laws of motion and utterly changed how things are looked at in the world today. All right? So on the top, or at the right under the quote, there's a lovely quote too, but right under the quote is the kinematic sample problem, and I'll let you work on that yourself. Submit your answer on Schoology if you would. Just let me know if I'm still going to be around on Monday, okay? I'm taking the parachute jump over the weekend.
There's no assignment.
What's that?
There's no assignment to submit it on.
Send me a message.
We're submitting the kinematic sample problem?
Yeah, and it's kind of just for fun. But you should do the problem, again, just for fun. Now, you see you're going to have to convert miles to meters. Do you know how to convert miles to meters? It's on... Yeah, you just keep multiplying by 1. And the conversion that you might need is centimeters to inches. That's 2.54 centimeters per inch. Then you know it's 12 inches per foot, 5,280 feet per mile, and 100 centimeters in a meter. That gives you everything you need, and you can find out if I'll be here on Monday. All right, and have fun with that. So we get to Newton's first law. Newton's first law is all about inertia. All right? Inertia. And I'll put it this way. This allows me to ask a million questions on CASA Learning because they're all trying to confuse you on inertia. And inertia is so simple that they got to really throw a lot of twists and turns to try to confuse you on a question. It goes like this. Inertia is proportional to mass. And period. Period. In other words, that's it. That's the only thing that inertia is proportional to. So in class earlier today, I picked up this and picked a student who wasn't paying that much attention, said, hey, catch, and threw it at him, right? And they caught it, right?
Yeah.
Can I get fired for throwing this at somebody?
If it injures them. Where are you throwing it?
It's a little ball filled with like foam things. Could I possibly, what would I have to do to injure somebody? I'd have to I don't even want to think about what I'd have to do to injure somebody with this. This is nothing. If I beamed you in the head with it, is it going to injure you? No. On the other hand, I have a rock hammer. Now, if I chuck the rock hammer at somebody,
Oh, yeah.
am I going to be here on Monday? I think yeah, right? I'm going to have somebody, Mr. Haberly is going to come and talk to me. I might even get talked to by Mr. Plesha. So the whole point is that the inertia is how easy it is to start and stop something from moving. This coming at you, even if you successfully stop it, yeah, I'm going to get talked to by somebody. There's a lot of inertia. You have to work very hard to stop this. Your head can hit this. No incident here. I don't have to fill out any paperwork. Like people giggle, right? Low inertia. Inertia is all about how hard it is to change an object's motion. If this is coming at you, it's incredibly easy to change its motion. If this is coming at you, it's a little bit harder. Imagine a locomotive moving at 1 mile an hour. It's only 1 mile an hour, so you get out in front of it to stop it. Are you stopping it?
Maybe after a very long time. It's a train.
Okay.
No.
Right, yeah.
Very slowly getting...
Liam is kind of correct that, yeah, if you keep pushing on it for, 30, 40 miles maybe, maybe, but you'll get tired and it'll just run you over after a while.
Oh, yeah. Very
So a locomotive moving hardly changes its motion at all. My father-in-law used to work for a port manufacturing company. He actually designed and built ports. And he was in Taiwan, and they were asking him to see if he could use some of his brilliance, which is considerable, to figure out how they could get the roads less congested. And he sees the roads are filled with trucks. Such a manufacturing society, there's trucks all over the place. The rail service is excellent there, but the rail service is closed at night. So what did he do? He said, well, why don't you take all the cargo on your trucks, put it on rails, and transport it at night? So they sent him to England to buy trains. He got to go and buy trains. Not something you usually do. But in doing that, he got to learn how trains, he got to learn how trains really work. And one of the things he found out that was a bit of a surprise was when you get a train up to speed, very often, for a good percentage of the time that the train is moving, the engineer kicks it in neutral. Now, when you have a train, a locomotive with hundreds of cars on it, and you get it up to 50 miles an hour and then you put it in neutral, what happens?
It's going to keep going.
Yeah, nothing happens. It just keeps going. It will tend to keep on going. Why? Because it has enormous mass, therefore enormous inertia, right? You're not going to easily affect its motion. And if you got in front and tried to stop that, one engineer would look at another and say, hey, did you hear something? Right? Oops.
Also, the front of the thing has a new red paint job, so that's cool.
Yeah, so like word unto you, don't do that. I'm not going to do that again. Not ever.
Oh yeah, I was planning on it. Wait, did you say it again?
Oh, wait, what?
So that's Newton's first law. All right. Newton's second law. I want to show you that you already know Newton's second law. Okay, so answer the following little questions I got. All right? So Newton's second law. If I take a force, and I want to see how the force is proportional to acceleration. So if I double the force on the same object, how much more will it accelerate?
Twice as fast.
Twice as fast. You already knew this. 3 times the force would give me 3 times as fast, right? So we see that force is directly proportional to acceleration. If I want the same acceleration, what do I got to do to force to get something the same? If I double the mass, how much more force do I need to get it to accelerate the same? That's what I'm on about.
Twice the force.
Twice the force. So they are directly proportional. That's why I wasn't getting this to work. Force and mass have to be directly proportional. What I'm seeking here at the end of the day is how is acceleration proportional to mass? If I double the mass, what will happen to the acceleration for the same force?
Halves it.
Halves it. So acceleration is inversely proportional to mass. So when I play with all these things, there's a way to put them together in the tiniest little formula, and that is Newton's second law. And I tell you, Newton's second law is one of the first places you see that the mathematical version of the law is so much easier to deal with than the English version of the law. And that's kind of fun to see. So the law comes out to F equals ma. And if I say it, force applied to a mass will produce an acceleration which is proportional to the force and inversely proportional to the mass. It's not so easy. On the other hand, F equals ma, got it. So this is going to give us a new unit. What are the units of mass that we normally use?
Grams?
Well, we use 1,000 of them.
Kilograms.
Kilograms. In earth science, we usually used grams. Here in physics, we always use the SI unit of mass as kilograms. What's the units of acceleration?
Meters per second squared.
Meters per second squared. So if we multiply these through, we get a kilogram meter over second squared. And we have a new name for what that equals. That is now and forevermore called 1 Newton. So a Newton is a unit of force. The unit of force you would need to apply to, like in floating in space, not in Earth, you would have to apply that to a 1 kilogram mass to accelerate it constantly at 1 meter per second squared. So, got a question. Here is a kilogram mass. This mass is 1 kilogram. I am on planet Earth. Little caveat. I'm standing here on planet Earth. How hard up, how many newtons of force do I have to apply to hold this from falling? Take a second.
You said 1 Newton it only counted if it was in space, right? Like no atmosphere, no gravity, no nothing.
Right? No gravity. No, nothing.
It's a little more than 1, isn't it?
10 newtons?
No, it's a lot more than 1. What gravity field am I in? What's my acceleration due to gravity?
9.1
meters.
Approximately?
meters.
Approximately 10 meters per second squared. So approximately how many newtons do I have to push on a 1 kilogram mass to keep it from falling in Earth's gravity field? 10 newtons, right? So this mass has a weight of 10 newtons. And look at what that gives us right away. So we have F equals ma. One of the first applications of it is to talk about weight. Now weight is a force, right? Which way is this force acting? Down, exactly straight down. All right.
Is weight just a force that's going straight down?
You got it. Weight is due to Earth's gravity field on a mass acting straight down. So weight is Earth's gravity field working on you and pulls you exactly straight down. So we derive a way of looking at weight from F equals ma. So your weight equals your mass. Are you on Mars? No. Are you on the moon? No, you're on Earth. So what do we approximate? Well, what do we...
G.
Exactly. The acceleration due to gravity, we put down as little g. So F equals ma, another way of saying that when we apply it to a mass, is that the weight of that mass is equal to the actual mass in kilograms times the gravity field you're under. So on the moon, you have an acceleration due to gravity of 1.6 meters per second squared. What would the weight of this object in newtons be on the moon? In other words, how hard up would I have to push on it to keep it from falling?
1.8 newtons?
1.6 newtons. It's 1.6. So 1.6 newtons,
I misspoke.
right?
Okay.
1.6 newtons. If you were on a planet with a bigger gravity field, you'd have to obviously push up harder. This would have a different weight. So your weight changes depending on what gravity field you're under. Does your mass change based on gravity field?
No.
Not at all. When we launch an astronaut into space, does her weight decrease? Not unless she has a real bad time with the launch. So mass does not change, but your weight certainly would when you go to a different gravity field. All right? So that is Newton's first and Newton's second law. The other thing with that is we have to think about things a little bit more deeply. And if I am suspending something on a string, if I have a block suspended by a string, I am pulling up on the string to suspend it. In other words, its weight is being transferred on this cable. This cable is under tension. I am pulling on it. Now, there are some materials that work fabulously well under tension. Fishing line. You don't push the fish away from you. That would be compression. This doesn't do well with compression. But under tension, heck, this line works tremendously well. What are other materials that you could imagine work really well under tension? Well, imagine a huge arch and you're suspending a bridge under it. Would you suspend it with concrete pillars? Would concrete work well under tension?
No.
No, you can see immediately. Those concrete pillars would break apart. The bridge is in the water. What do you rather, if you have an arch, what do you suspend the bridge from it with?
Steel cables?
Steel cables. How do steel
Braided
cables
steel
work?
Cables.
What's that?
Braided steel cables.
Braided steel cables, that's exactly what they use. How well, and they could really use steel rods too. They've used that in the past. How well does steel work under tension?
Very well.
Really well. How well would steel rods work under compression?
Not so good.
Not so good. They would bend in half. It wouldn't work at all. Would those concrete pillars work good to set the bridge on?
Yes.
Yes, they would. So concrete works really well under compression. So we start thinking of how we transfer these forces. That's one of the things. But one of the fun applications of this is the elevator problems, right? And we're thinking weight equals mass times gravity, and we're thinking tension, because the tension on the cable holding the elevator is what's holding you up. So think of this. If you step on a scale that's reading your weight in an elevator, and that elevator starts going down suddenly, what happens to your weight?
It decreases.
It decreases. So,
You seem to decrease because the elevator's going.
right? If you're going down, your weight is going to seem. It doesn't actually, but it's going to seem like it decreases. Actually, no, I think you could say your weight temporarily decreases. Because while you might be in approximately 10 meters per second squared, if you're going down accelerating at 1 meter per second squared, you'd be subtracting from that 1 meter per second squared. So now your weight would only be 90% of what it was before. On the other hand, if you were going up, if you're accelerating up, you're already having to push against the floor with whatever you need to deal with the 10 meters per second squared gravity of Earth has on you. And now you want to increase by accelerating upward at 1 meter per second squared. So you could, I think, see that you'd have to add that on. And that is what the scale would now read your weight to be. You've increased it by 10%, at least while you're accelerating. But be aware, once you're at constant speed, can you even tell that you're moving in an elevator? Nope, there's no way to tell. No experiment on Earth could tell if you're moving at constant speed and you're all closed off from the world around you. It's only when you stop or accelerate, only when you change your motion, that you could be aware that something is going on, that somehow you're moving.
What's change in acceleration?
Change in acceleration. Yep. That's how you could tell. I was asleep once in the back of my car with my parents driving when I was a little kid. And I was lying there and I had woken up, but I was still lying there looking at the back seat. And I was starting to wonder why we're stopped for so long. This is odd. And all of a sudden, I was pulled towards the front seat as my dad tapped on the brakes a little bit. We were at highway speed, moving at 55 miles an hour, and I couldn't tell. Not until he changed the speed. And I was suddenly pushed towards the front seat a little bit because we were slowing down, like that coffee cup acceleration thing. So moving at constant velocity, there's no way to tell. Only in an acceleration can you tell that something's going on. All right? That is the entirety of mechanics number 6. Any questions?
No.
Nope.
You guys rock. If you have any questions, please let me know on Schoology. I am here for you. I do work for you guys, so any question you have, I'll do anything I can to try to help you out. Okay?
All right. Thank you.
Anything else? I'll talk to you.
I think I'm good for now.
Thanks.